Hello. I'm going to go ahead and do an example problem that uses Newton's third law of motion for a change, and it also uses Newton's second law as well, in both conjunction. I already have the free body diagram here. The mass of the woman isn't as much as the mass of the man, so the normal forces aren't equal as well, but that is irrelevant actually for this problem. It's only accelerating in the both of them are accelerating in opposite directions. But since this is an example of Newton's third law, the action force is equal and opposite to the reaction force. That's my symbol for action and reaction. Okay? So let's see what we're given here. Given the mass of the man, it's just capital for some reason, the mass of the woman, okay, I'm going to change that. Mass of the man, mass of the woman, and the action force actually comes from the woman, and in the positive direction, newtons, and the positive x direction, and then it's frictionless. Good, because friction would complicate the problem. We're actually solving for three things here, one which almost immediately comes to us. A is the acceleration of the man, and B, the reaction force, and C, the acceleration of the woman. Okay? So the formulas that we need are quite simple. It's just Newton's second law, in this case just in the x, no acceleration in the y, and that Newton's third law for a change. And for every action force, for a force interaction, there's an equal and opposite reaction force, equal in magnitude, exactly opposite in direction. So yeah, let's just go in order. Let's go in order. I can even start the solution right here. So solving for the acceleration of the man. Acceleration of the man, if I use this formula, I can switch it around. If I divide both sides by m, is the acceleration, sum of all the forces in the x divided by the mass. In this case, there's only one force, the action force, divided by the mass of the man. And so that's 85 newtons over 75 kilograms. But remember that newtons is actually kilogram meters per second squared. So that cancels that out and leaves us just with the unit of acceleration. Okay? And the direction of the acceleration will be the same direction as the force. So in this case, it's going to be positive 1.13 seconds squared. Acceleration of the man going in that direction. And B is actually the easy part. The reaction force that will accelerate the woman is just equal and opposite to the action force rather, and so it's just simply negative 85. Okay, so that's pretty simple. But since the woman weighs less, we're expecting her acceleration to be more. She's going to go faster. And so hers, the Okay, and so now that is negative 85. We're actually going to keep the negative divided by the 55. Once again, taking that, leaving us with units of acceleration. And the acceleration of the woman is negative, but it's actually more. Okay, so it's a good example. Shows that when the mass is less, here in this case for the same magnitude of the action force, acceleration is greater. For the same force with a greater mass, the acceleration goes down. Okay, so the woman is accelerating towards the left. Okay, and that's pretty much it. A very simple problem that uses both Newton's third law of motion and Newton's second law. Okay, enjoy.